So let's start. And I formulated last time the next theorem we're going to prove. So let me recall it now. So we have a projective variety x, and a coherent sheaf f. So there's a finiteness theorem that says first that any cohomology group is finite dimensional, and in fact we know that here I goes from 0 to to capital N, where x is embedded in the projective space and dimensional. But anyway, and also if we twist our f by a very positive line bundle, the higher cohomology will be 0. So there will be some global sections, but no higher cohomology. Okay, so let's prove this. Well, we have x embedded into the ambient projective space, and we can consider the push forward of our coherent sheaf, and this will be a coherent sheaf on Pn. So it's enough to prove the theorem for this push forward, and so it's enough to assume that X is just the projective space. But X is the ambient projective space, and F the coherent sheaf. Okay. Now, this is a very typical method that we will encounter once again later on today. The proof goes by induction in the number of cohomology, but it will be the descending induction. So not from I equals 0, but from I equals capital N. Okay, so we know that if this number of cohomology is bigger than capital N, then cohomology just vanishes. So both A and B are true, and we can start our induction going down. And to this end, recall from our early days about coherent sheaves that if we twist F very positively.
Извините, а мы вроде базу индукции доказывали там на прошлой лекции только для F, когда O(n), ну то есть структурный пучок твистованный.
No. We compute explicitly all the cohomology of invertible sheaves. You're right, but then we introduced this calculational tool of Czech complex, Czech cohomology. Yeah, and this was a resolution of any quasi-coherent sheaf, and this resolution had some bounded length. Namely, the length was equal to the number of open sets in our covering. And for example, for projective space, it's enough, say for PP capital N, it suffices to have n plus 1 sheaves to cover, right? Sorry, n plus 1 open, affine open subsets, the cells, standard cells, to cover the ambient projective space, right? And since the length of Czech complex is n, capital N, it cannot have cohomology in degrees higher than capital N, right?
Спасибо.
Welcome.
And also, I have a question. How do you reduce the general case to the case of Pn? So
just by taking the push forward of any coherent sheaf on any projective variety. This push forward will be a coherent sheaf on P on the ambient projective space, and its cohomology will be the same as the cohomology of the original sheaf F.
I just forgot why is it so? Why is the cohomology?
Well, if you wish, because the closed embedding is an affine morphism. Yeah, and for affine morphism, you can compute cohomology over sheaf in terms of its push forward. Yeah.
Okay.
So maybe I should add it somewhere here. A closed embedding is an affine morphism. Sorry. Okay, so now let's get back. And I was saying that for a very positive twist, the twisted sheaf f of n is generated by its global sections. So we have a morphism from some finite dimensional vector space. Yeah, these global sections form a finite dimensional vector space, tensor the structure sheaf, and there is a surjective morphism to f of n. Yeah, when we described the coherent sheaves on projective varieties as sort of localization, yeah, with two graded modules. Then these graded modules were finitely generated, and so the generators occurred in some finite number of degrees up to this small n, and this small n would work. This is an outline of this old argument. So we have this, and now let's untwist back, and we get an exact sequence. There will be some kernel here, and then there will be well, a few copies. Maybe let's call it V tensor O P n of something P, and this P will be negative n, and then it surjects onto F. There we are. And this case really,
как она работает?
Well, I don't know how it works, but you just take the above surjection, you untwist it by n, yeah, then f of n becomes f, and O becomes O of negative n.
Спасибо.
Okay? And k by definition is the kernel, and the kernel of morphism between two coherent sheaves is necessarily coherent. Okay, and then we're going to compute as well. We're interested in cohomology of f, but But in the middle, you have some vector space V, which contributes only multiplicity, and some invertible sheaf may be very negative. Yeah, and we know that any invertible sheaf only can have cohomology in degree 0 or capital N. And in fact, if it's negative, then it's only in 1 degree, capital N, only the highest cohomology, right? And then from this long exact sequence of cohomology associated to this short exact sequence, we obtain that from our knowledge of cohomology with coefficients in invertible sheaves, we obtain the long exact sequence of cohomology gives, say, for any I that is smaller than capital N, we get an isomorphism from I minus first cohomology with coefficients in F to ith cohomology with coefficients in K. Okay, and well, now if I is capital N, then we get an embedding from H n minus first cohomology with coefficients in F embeds into the highest cohomology with coefficients in K. Okay. Now we wanted to prove that cohomology is finite dimensional, right? And what do we know? Well, we also need one more thing. Unfortunately, I have to turn the page. And let me write down one other surjection. So this V tensor, the highest cohomology of Pn with coefficients in of P, this negative invertible sheaf, surjects onto the highest cohomology of Pn with coefficients in F. Okay, well, let's have one last look at this short exact sequence and see that it gives rise to these three things. So isomorphisms of cohomology in the middle and some embedding in the top and some surjection in the top. And now this is finite dimensional. And hence this dimension is also finite. And if we go back, so we proved this finite dimensionality of the highest cohomology, of the top cohomology, for a coherent sheaf F. Okay, for any coherent sheaf F. In particular, we can take K for F. Okay, so this rightmost thing in the lowest row is finite dimensional. Hence, the n minus first cohomology of F is also finite dimensional. And then we proceed by this descending induction and see what that all cohomology finite dimensional. Okay, so we proved A. And now we have to prove B. What was B? B was the claim that the higher cohomology of sufficiently positively twisted sheaf vanishes, and Again, B follows the same way.
Можете, пожалуйста, еще раз пояснить, почему вот размерность V тензор HN от Pn от P, вот то, что сверху, почему оно конечномерное?
Just because the last time we computed all cohomology of all invertible sheaves, right? So any invertible sheaf, O of P, has some cohomology we explicitly computed. It was some,
Ну да.
yeah, some.
А V почему конечномерное?
Homogeneous. Well, because this V was just the space here. This thing is V. Okay. V is the global section of global sections of our twisted sheaf. Yeah, and twisted sheaf is coherent, and the global sections of any coherent sheaf on a projective variety is always finite dimensional. This was also proved a long time ago. So we proved this for H0, and now we proved it for arbitrary cohomology, but somehow not starting from H0, but starting from H top. Okay, this is an interesting trick. Okay, so the proof for B go the same way, or only well, based on this fact for invertible sheaves. So the higher cohomology with coefficients in a line bundle, maybe let me call it L. If you twist it sufficiently, then we'll get 0. So here n is very positive, and L is invertible. So it's isomorphic to O of something. Okay. Fine. So we prove this finiteness theorem. And well, one thing it allows us to do is to define the Euler characteristic, as we did for curves. So this is the dimension of the global sections, or maybe let me write down. Ith cohomology with coefficients in the usual Euler characteristic. So all the cohomology are finite dimensional, so this makes sense. Fine, and then also we can define the Hilbert polynomial.
А знаков нету в Эйлеровых характеристик?
Sorry, yes, absolutely, yes. -1 to the power I. Sorry, thank you very much. Hilbert polynomial PF, well, of R is the Euler characteristic of n with coefficients in F twisted by R. And well, there is a lemma or whatever claim that it really is a polynomial. Of degree not more than capital N, and in fact this degree is equal to the dimension of the support of our sheaf F. Okay, but maybe I will not prove this lemma now. I hope we'll study Hilbert schemes maybe in a month or so, and then we'll talk more about it. But in fact, in some exercises, you already proved it essentially, because you know that when you twist your sheaves sufficiently positively, then there is no higher cohomology. There is only dimension of global sections, nothing else. And for the dimension of global sections, you proved already in some home assignment that this gives you a polynomial. And then you only need to check that this polynomial works for Euler heuristic for arbitrary twist. Okay? So what you had in home assignment was sort of poor man's version, when we didn't have notion of Euler characteristic. Then we had to use the high enough twist, positive enough twist, in order to compute just global sections. But you don't need to go far into the positive range if you use the notion of Euler heuristic. It's much more natural. Okay, so we have this. Also, there is the general Riemann-Roch Hirzebruch theorem that computes the Euler characteristic of any coherent sheaf in terms of its Chern character or whatever, Chern classes. And well, I will not explain what it is. For the sheaf, for a sheaf on a curve, there will be only first Chern class, and it is given by the degree of your coherent sheaf on a curve. And these are some higher dimensional and higher cohomological generalizations of these notions of degree. But well, maybe the most important message is that say if your sheaf F is just a vector bundle on the whole of Pn, then somehow its Chern classes are of some topological nature. So they're very rough topological invariants. But the Euler characteristic is of algebraic geometric nature. Yeah, it's some coherent sheaf thing. And so the importance of this Riemann-Roch theorem is that you can compute something algebraic geometric in terms of something topological, and it's a miracle that the two things match. Okay.
But
Yeah.
you know the notion of Chern class for say vector bundles, but are there can it be extended to any?
Absolutely, yes. That's what probably Grothendieck did in his early days, because the Chern, whatever, I don't know, let's say Chern character is additive, right? And so it extends to the K group, Grothendieck group. Yeah, well, in fact, Grothendieck introduced this notion of K group just for this, just for extending Chern classes to arbitrary coherent sheaves.
I heard that there are two different versions of K group due to Grothendieck and maybe Atiyah.
Well, Atiyah just transferred the Grothendieck definition to topology.
Yeah.
Yeah, but here we just work with locally free sheaves on projective varieties. That's the version we use. And then there is some other version for coherent sheaves, but say for smooth varieties they coincide, like for projective space. And the one we need here is the vector bundles, locally free sheaves.
So you say that the Chern character can be defined on the Grothendieck group, and
absolutely, yeah.
any coherent shifts has its image in Grothendieck group, so it
Yeah.
okay.
Mm-hmm.
I see.
So is the
Yes.
Chern cross defined with coherent sheaf, but sorry, what does depend on Chern classes? What is the variable with Chern classes? Is it quasi-coherent sheaves?
I'm confused. So once again, given any coherent sheaf, you can define its Chern classes, and they will be elements of, say singular cohomology. If we are over complex numbers, then they will be elements of the classical singular cohomology of projective space.
Okay. So it is functor between what sheaf and cohomology group or abelian group, right?
Well, so to say, yeah, to any coherent sheaf, you can associate some elements in the singular cohomology groups of projective space.
Okay, thank you.
But not, in fact, not necessarily singular. Any reasonable cohomology theory will work. Say the RAM cohomology or Joe groups, whatever. Fine. Let me recall these are topological invariants. If our ground field is complex number. Okay, so once again, the miracle here is that you compute some algebraic, geometric quantity in terms of purely topological invariants, very rough things. Already for curves, this is miraculous, that you can compute the algebraic geometric Euler heuristic just in terms of very rough invariant, the degree of your locally free sheaf on the curve. Okay, so now let's do a cheap generalization that will turn useful. Generalization. Maybe relativization. So now we have a projective morphism. So before we consider just X, and we had a projection, its projection to a point. And now the situation is relative. So we have X and projection to another variety, but it's a projective morphism. Okay. And again, we have a sheaf in the, well, a coherent sheaf on X, and the generalized theorem says that for any I, the higher direct image F is a coherent sheaf on the base, and also for big enough twist, these higher direct images, positive, really higher direct images of your sheaf twisted all vanish. There is only the direct image, the zero, well, the zero derived functor of direct image. Fine, so it's just an immediate generalization, and the proof is also immediate. So first of all, when I say that F is projective morphism, what do I mean? Well, I mean that we have the product y times some big projective space, and a closed embedding from X to this. Let's call it U again, and then we can go from our coherent sheaf to its push forward on the product, and so we can assume that our X is Y times projective space, and F is just projection onto Y. Okay, and now now the both claims A and B are local along Y, so we can assume that Y is affine, say, spectrum of some ring A, and then we know that we already know that all those higher direct images are quasi-coherent sheaf, right? So they let's write it down. That they are quasi-coherent. So there's localization of something. M tilde or M just a module over A. Okay, and we all need to prove that those models are finally generated.
Sorry, I have a question in regard
Yes.
to Chern class. Is it possible?
Yes.
So I believe Chern class in differential geometry is defined on vector bundle, but like,
Right.
is it appropriate to say like quasi-coherent sheaf in our algebraic geometry? Because I think vector bundle is free module in algebraic geometry. So this is my question.
Yes. Thank you. So I had to prove that M is finally generated. Okay, and then again, we know that this M is just global cohomology, namely ith cohomology of Y times Pn with coefficients in our sheaf F. Okay, and now we only need to develop. Well, if you go through the proof, then you essentially the only thing we used was this short exact sequence. Let's have a look. Yeah, here from twisted structure sheaf to F with the kernel K. Okay. So the proof is word for word. Repeated. Well, from the case y was the point, and we only have to know that there is a short exact sequence like there. Okay, so some pre-module V tensor O n times y P then goes to F and goes to 0. So V free a module. Okay, or maybe not even free. Maybe we won't. Sorry, we don't even need to know this. I finally generated a module. It's a free.
А как определяется теперь, это вообще произвольный модуль V, или он тоже имеет определение в виде сечения?
Who is V? No, just the same. V is the global sections of P n times y with coefficients in insufficiently twisted. Okay.
Спасибо.
And well, as I mentioned in the very beginning, when we constructed this Schrodinger sequence, you only need to know that any coherent sheaf F on a projective space is, well, after sufficiently high twist, is generated by its global sections. So again, it suffices to know that F is, well, F of n is generated by its global sections. For sufficiently positive twist. And then the same theory of localization works for the projective, for coherent sheaves on Pn times y, as for coherent sheaves on just P. So I mean, you consider the graded, positively graded modules over so before we had just vector spaces, and now instead we have just a modules. Sorry, a modules, and they give rise to coherent sheaves on Pn times y. Okay, so what essentially what happens? We replace K by A, and vector spaces over K were replaced by A modules. But then everything goes through just for the same price. Nothing changes. Okay, and in particular, the proof of this theorem goes through. So this is it for this relative version, and it will be used soon because now we're turning to the study of such relative situations. So the morphisms from X to Y, and well, we view such morphisms as families of fibers. X, Y, where Y runs through the point in the base. And then, well, for example, given this, you can consider many associated families, like family of cohomology of fibers, or something like this, or cohomology of fibers with coefficients in some sheaf, that is also, say, family of sheaves over the fibers. So there are many families around, and then the historical experience eventually showed that some families are really families, and some don't even deserve this name. So the key word here is flatness, and well, let me write this word: flat morphisms. Like F, well, can really be called families, and otherwise, well, not. So, for example, we can consider just the disjoint union of fibers, and the disjoint union of fibers, in no sense, will be a meaningful family. Yeah, we somehow need some smoothness going from one fiber to another. And initially, it was not clear. Well, say in the classical differential geometry, there is no notion of smooth morphism, and that's a good family. But also, you can have some degenerations, like the famous picture like this. Yeah, when a hyperboloid degenerates into a cone, something like this, over the base. And there's not a smooth family, but still it's a nice family with degeneration. You can compute vanishing cycles in this family. It makes sense. So you need some notion of family, and even in differential geometry, it's not quite clear. So it's more general than smooth morphism. But what a morphism do you really allow? And in algebraic geometry, there is a standard answer. It gradually became clear, like maybe 70 or 60 years ago, which morphism, which families deserve this name. Okay, so let me give a definition of flat morphism now. And maybe even, well, okay, let me give this definition first and then generalize it. So for any point x in X, and then y equals f of x, the local ring O XX is a module over O YY, and this module is required to be flat. And flat, it means that say an A module for any commutative ring without nilpotence. And in fact, here it's not essential. Any commutative ring at all, say M is flat if the functor of tensor product is exact. And recall that it is automatically right exact. But we require it to be left exact. That is, we require it takes injections to injections, yeah? Embeddings to embeddings. Okay, so this is the definition. And maybe this was part A, and part B, more generally, if F is a quasi-coherent sheaf on X, then it is flat over Y if any stock Fx is a flat OY module. Okay, so this definition, and once again, let me stress that from this definition by itself, it is absolutely non-clear why on earth should one study these things. Okay, it only somehow happened historically that after many tries and takes, the people realized that this is a good notion. There is, at least for me, there is absolutely no intuition behind. I only learned, many years ago that it's a good notion, but there is no a priori reason that we should study flat sheaves. Okay, so now let's maybe reformulate this definition globally. F is flat over Y if and only if for any open affine subvarieties U in X and V in Y, such that U projects onto V. The global sections upstairs with coefficient F is a flat module over the structure sheaf downstairs. So K of V module. Okay, and the proof is immediate. So in one direction, so the global to local. Just because localization is an exact functor, commuting with tensor product. Okay, so the stock is just the sections over some, well, the co-limit of sections over shrinking the neighborhoods. So you localize, and if you know that all the sections in this co-limit are flat modules, then their co-limit will be again flat. Okay, but local to global. So we would take any module M over the open set in the base. And we want to see that the tensor product with this M is exact. Okay, so we see that the global sections of U with coefficient in F, tensor with M, is the global sections of U with coefficients in F, tensor, the pullback of say localization of M, if you wish.
А почему такая формула получается в последнем?
But it's just by definition, I would say. Maybe you may call it projection formula, but it's just by definition. If you unveil if you recall the definition of objects here, you will just see this.
Откуда локализация появляется?
But you have to apply your pullback factor to a sheaf, right? And so far you're only given a module over the global sections. Yeah. So you have to first localize it, then pull it back. But in reality, this is computed on the global level, and it's just, if you recall the objects involved, it's a tautology. Welcome. So we know this, and so then we know that the M goes to global sections. Tensor M is the composition of exact functors namely M goes to its localization, and then this localization goes to its pullback, yeah, tensor F, and here you use the stockwise flatness. Okay, you only need to check the exactness on stocks, and you know that at the level of stocks it works. And then maybe again global sections. What did we use there? Global sections of this, right? Sorry. Whatever goes to global sections of U here, and it's exact since U is a phi. Okay, so this tensor product functor is exact as the composition of three exact functors. Three exact functors. Okay, so the lemma is proved, and maybe let me make a remark that, for example, if f is the structure sheaf of x, and x to y is a projective morphism, so recall it means that x is embedded into y times some big ambient projective space and then projected to y, and this composition is just called f. Okay, so in this case, remember that remember that we had the notion of Hilbert polynomial. Yeah. So I say that OX is flat if and only if the Hilbert polynomials of all the fibers are the same. And the same for more general f. Sorry. Okay. So for arbitrary f, the Hilbert polynomials py of don't need the Hilbert polynomials of xy with coefficients in f restricted to xy must be constant. Oh, sorry, it's independent of y. So in particular, OX is flat implies that the dimension of all the fibers is constant.
Почему так случилось?
Because we know that the dimension of the fiber is the degree of the Hilbert polynomial. So if the Hilbert polynomial is independent of the point and the base, then in particular the degree is independent of the point and the base, so the dimension is constant.
Необходимы достаточные условия для того, чтобы структурный пучок был плоским. Почему такое?
It's an interesting theorem, and we will not prove it. Maybe I will give it on home assignment at some point. Okay, but
Хорошо, спасибо.
Or rather, we will prove it when we do Hilbert schemes. Okay. So in particular, the blow-up morphism, 0, say, of affine space goes to affine space, is definitely not smooth. Not flat. Because all the fibers are just one point, but at the origin, the fiber is projective space of bigger dimensions, so it's not flat. So the dimension of fibers should be constant, and it's a necessary condition. But under some favorable circumstances, say both x and y are smooth. It is also sufficient. So all the fibers have the same dimension. So it is independent of small y, implies that f is flat. Okay, so in other words, OX is flat over y. Okay, so, well, it's somehow it seems that it's much more rough, but in fact, just this suffices. And this does have some intuitional meaning. Yeah. So in your family, at least the dimensions of the fibers should be the same. Okay. And so now let's start proving Grothendieck theorem. Maybe that's really a first theorem by Grothendieck that we study. And as many Grothendieck theorems, it looks rather abstract. But then we'll see already next time that it has very powerful and useful and numerous applications. But just it is very general. So Grothendieck looked at the very core of things. So if f a coherent sheaf on X is flat over the base Y, and recall that X to Y was projected. Then any point in Y is contained in an open neighborhood U, where we have a complex K0, K0, K1, and so on, then Kn to 0 of three OU modules of finite rank, computing well the complete the full direct image of F tensor, the pullback of any module proceeded to U. So let me say what I mean by this. So we had this flat sheaf on X. So we also have an arbitrary coherent sheaf on Y. And when I say that this complex computes this full direct image, I just mean that for any I, ith direct image of F tensor, the pullback of M over U is the ith cohomology of this complex. but by cohomology I mean well, a coherent sheaf on the base, well, on U. So I don't want to compute whatever global sections and its derived functions. I just have a complex of sheaves, and I take its cohomology stockwise or whatever. So it's a coherent sheaf. Maybe local cohomology. I don't know how to say it better. I use this underline to stress that it's local cohomology. Okay.
Local means cohomology is a complex.
Yes, the cohomology is as a sheaf, as a coherent sheaf.
Okay, so it is a complex of something, and you take a cohomology.
Yeah.
Okay.
So if I have D, then this is like the kernel of di over the image of di minus 1. Yeah. Okay. So in other words, well, it's a local statement. Yeah, you chose a neighborhood of a point, but globally it means that there is a complex of locally free sheaves. Okay. So let's start proving, and I guess we will not succeed today. It's not a difficult proof, but takes maybe not 10 minutes, but 15 or 20 minutes. So
Сейчас я не очень понимаю, а почему нельзя взять m просто совсем нулевым?
Okay, to be
И
absolutely
тогда
zero.
теорема ничего не утверждает.
No. We want to compute this. Okay? We want to compute this, right? And the claim is that this thing is computed by a bounded complex of finite rank free OY modules, OU modules.
То есть m задан заранее, да?
Yes. M is
Хорошо,
fixed,
да.
and F is fixed. Maybe I should put this M.
Спасибо.
Yeah, and then remove it from here. Okay, so there is some coherent sheaf on X, some coherent sheaf on Y, and I want to compute this thing, and it is computed via a bounded free complex of finite rank. Okay, so again, the statement is local on Y, so we can assume that Y is affine. And since Y is affine, all the coherent, quasi-coherent sheaves here are global sections of localizations, and then
Почему последнее утверждение локально?
Well, just by the very statement, yeah, you need to find neighborhood. This neighborhood can be a small affine neighborhood. This U, yeah, this U can be small affine, and it can be taken inside any other affine neighborhood. So
Да, спасибо.
Definitely affine. So it's enough to check this for global sections of Y with coefficient in something. So in other words, we need to produce a complex K of A modules where A is the ring of regular functions on Y, computing the cohomology of
Нам же надо, чтобы было, нам же надо модуль надо O от U, а здесь получается модуль O от A. Да?
But once again, if U is equal to Y, then it's very good. Yeah.
Да.
We're in business. Well, this Y is U. Okay. And the cohomology of X with coefficients in F tensor the pullback of M. Well, computing this as A module. So that's what we have to compute. And we will compute it using Czech resolution. Okay, the technical tool introduced last time will allow us to prove this technical theorem of Grothendieck this time. So we compute this cohomology via Czech complex. And now we take a covering of X. This, so it's an open affine cover. And we proved last time that the cohomology coherent sheaf
должно быть отделимо для того, чтобы применять.
Right. Right. So well, okay. I should have written it explicitly somewhere. So this is separable. But maybe no. But the statement is local. You see. So maybe I shouldn't even write this. Sorry. Because the statement is local. Locally, Y is affine, but the morphism was projective, and any projective variety is necessarily separable. Okay, so so it works without any additional assumptions.
Спасибо.
Welcome. So the cohomology of any coherent sheaf or quasi-coherent can be computed via this Czech complex. So the cohomology of X with coefficients F tensor pullback of M is the Czech cohomology. Only I forgot how I maybe like this cohomology of the Czech complex. Oops, sorry. Czech complex of this. Okay, and now we can extract this tensor from Czech complex. So.
Извините, а вот это К в теореме, которое было, К, это вот это комплекс Чеха?
No, unfortunately, no.
А что это?
Well, you see, it takes 15 minutes to prove this theorem, and eventually I will say what is K. So you will use this Czech complex, but this K is not literally this Czech complex. And for a good reason, because in Czech complex, you take some intersections of open sets in your cover, right? Well, for example, imagine that y is just a point, okay? Then those terms of complex k are just finite dimensional vector spaces. And already, in fact, already at this point, there is something to prove. Yes, when y is just a point, you want to compute the cohomology of sheaf F via a complex of finite dimensional vector space, right? But in order to be able to do this, you need to know that the cohomology are finite dimensional, right? And in fact, it's equivalent. So we did some work today in the beginning, yeah, to guarantee that the cohomology is finite dimensional. Okay, so this cannot come for free. You need to use something. And what we're using now is a Czech complex on X. So you cover your X. X is projective, but you cover it with the open spaces, and then you take sections on these open space or their intersections, right? But the sections on affine open spaces are definitely infinite dimensional. So your Czech complex is it's bounded, but all the terms are infinite dimensional, and still it computes something finite dimensional. Okay, so this desired complex K is some very, very strong truncation of your Czech complex. Czech complex is very big, infinite dimensional, but for some reason it can be truncated to something, to some complex, some much more economical complex with a finite dimensional term. Okay, and over a general base y, you have to replace with the words finite dimensional, but by the words free of finite rank. Okay, that's what we have to do. And well, we just have 2 minutes, so we don't actually do anything at all. But let me say that when you compute terms of this Czech complex, you take some global sections of some intersections, I0 intersects so on, I R, I don't know, sorry, with coefficients in F tensor the pullback of M, and then this is clearly just the global sections of the same intersection with coefficients in F, and then you just tensor over our algebra A with M. So here A is the algebra of regular functions on Y, and M is again the global sections of Y with coefficients in this sheaf M.
Локализовать нужно вот слева то что под сечением стоит. Сечение, пучок там стоит. Мы писали раньше, что мы локализовывали.
No, you don't. No. It's already localized. When I write calligraphic letters, it's already localized. I say that well, M straight is global sections of M calligraphic, and the M calligraphic is localization of M straight. Okay, so but I didn't even finish my sentence. Since we have this evident equality, it means that that the Czech complex of F tensor pullback of M equals the Czech complex of F tensor over A, just this M. Okay, so well, at this optimistic note, we have to stop today, but the next time it will just take us 10 minutes to prove Grothendieck theorem. Okay, so since we are able to extract M from this complex, that we only need to do something with this Czech complex of F, and we will do this next time. Okay, so thank you for today. Any questions?
So I have a question. So I wanted to ask about subtlety of vector bundle, concept of vector bundle in algebraic geometry.
Yes.
So what I wanted to say is that vector bundle is finite rank free module, and quasi-coherent sheaf is not necessarily a finite rank. So like, what is the subtlety?
No. But when you define K group, you don't use quasi-coherent sheaf. Otherwise, you just get 0. You only use coherent sheaf.
Oh,
and also there are two different notions of K group. In one case, you only consider vector bundles or locally free sheaves and nothing else, and you only use exact sequences of such things. And there's another version where you allow arbitrary coherent sheaves and the exact sequence of those. And these are two different notions. But if your variety is smooth, then those two notions coincide. That's sort of Hilbert CZG theory.
Oh, I see. That's
okay. But in general, there is no reason for these two things to coincide, and they don't coincide in general.
okay. Thank you. It's very useful. Thank you very much.
Welcome.
Okay, and also I also have a question about Riemann-Roch-Grothendieck theorem. I thought, Hirzebruch theorem. So I thought that Hirzebruch was a topologist, but
yes,
you mentioned that this is an algebraic geometric theorem.
Yes, but the most famous book by Hirzebruch, I mean the one having thousands of references, citations, is called algebraic. Oh no, sorry, I forgot. It's either topological method in algebraic geometry, or maybe, yeah, I think it's topological methods in algebraic geometry.
Mm-hmm. So this is a really algebraic a theorem in algebraic geometry world, not a topological theorem.
Well, it's a very important, maybe a central theorem in many areas. And as such, it has very many proofs and very many points of view on it. So it lies at crossroads of very many areas. So there is a purely topological statement, like you can take the book by Fuchs-Fomenko and find their topological Riemann-Roch theorem. There is a purely algebraic statement due to Grothendieck. Say it's valid over arbitrary field, not necessarily complex number. And there are many other variations on this theme.
Okay, thank you.
Welcome. Okay, so if there are no more questions, let me save my notes. And let me stop the recording. And let me say goodbye.
Daniel.
To everybody.